For the last week or so, we've been looking at how net ionic equations help scientists with double displacement reactions to determine if a solid, a liquid, or gas is going to be formed. We're going to shift gears now and start to look at single displacement reactions. So how are those single and double displacement reactions different from one another? When you're looking at a double displacement reaction, it's always a compound plus a compound makes another compound plus another compound. So whatever the charge is of the ion on the left-hand side, it's the same charge on the right. They're just swapping places. They're not changing charges during the course of a reaction. But when you have a single displacement reaction, that's not the case. In fact, that's not the case anytime you start with an element and end as a compound, or vice versa. So like a synthesis reaction, for example, you start as an element, end as a compound. Or in a decomposition, you might start as a compound, end as an element. And so anytime you have that element-compound switcheroo, your charges are not going to stay the same during the course of the reaction. One key idea here to keep in mind is that all matter is electrically neutral. All elements, all compounds are neutral. Ionic compounds can have positive and negative pieces, the cation part and the anion part, but the overall compound is neutral. In just a minute, you're going to see a demo in class for the reaction between copper and silver nitrate. So we're going to write the balanced equation, the complete ionic, and the net ionic for this reaction. So we're going to use the element copper, standalone copper wire. So because it's a wire, it's a solid, and copper, the element, is neutral. The only time you can have charges is if you're part of an ionic compound where you have a cation part and an anion part. But because this copper is not part of a compound, it's just an element, this guy does not have a charge. So I'm going to put a 0 here next to the copper for emphasis. You don't have to write the 0 in the reaction, but I'm just putting it there as a little reminder to you that that copper is indeed neutral. We're going to react that with some silver nitrate. Silver is Ag plus 1, nitrate is NO3 minus 1, so we'll have AgNO3. If you look at your solubility chart, all nitrates are aqueous, and so we'll add that to our reaction. When we go to the product side, we have to decide who does the copper want to dance with, the silver or the nitrate. Well, in compounds, copper forms positive charges. Again, the element is neutral. In compounds, copper can have a charge. Now, if you look on the back of your periodic tables, you'll see that copper could either be +1 or +2. So how do we know which one it is? When we were doing double displacement reactions, because the charge didn't change, you could look at whatever it was on the left-hand side and assume it stayed the same on the right. But that's not the case for single displacement reactions. There actually is not a way for you to determine which one it's going to be. I would have to tell you. I would have to give you a clue. So this time, I'm going to tell you. When our copper becomes part of a compound, he's going to form a +2 charge. And so he wouldn't want to go with silver that forms a +1 charge. Instead, he's going to want to go with our nitrate. So nitrate's -1, copper's the +2 kind. So we're going to make CuNO3 2. Since all nitrates are soluble, this guy's going to be aqueous. And the silver gets kicked out by itself. The silver is not a Hofbrinkel, so we can just leave it as Ag. The state of matter of silver is a solid. If you weren't sure, you could look at the periodic table on the wall in the classroom and see if the symbol for silver is black for solid, blue for liquid, or red for gas. Again, this silver is an element. elements do not have charges. The number of protons equals the number of electrons. So this silver is neutral. The silver on the left-hand side, when it was part of a compound, that guy has a charge, but the silver on the right does not. We do have to balance our reaction overall because right now our nitrates are out of whack. So I'm going to put a 2 in front of our silver nitrate and a 2 in front of our silver, 1's in front of my copper 2 nitrate, and 1 in front of my elemental copper. There's our balanced chemical equation. Now we're going to write a complete ionic equation. When I do my complete ionic equation, we're going to break up anything that's aqueous, any solids, liquids, gases we would leave alone. So my copper, I'm going to leave alone, and I'm just going to leave that 0 there for emphasis, that's the neutral kind of copper. My aqueous silver nitrate would be broken up into silver ions, Ag+1, and nitrate ions, NO3-1. Both aqueous because they came from something aqueous, and we would have 2 of each. On my product side, my copper 2 nitrate is aqueous, so he's going to get broken up into copper ions. And again, this is the +2 kind of copper. There is no way for you to know that on your own. I would have to give you a clue. And nitrate ions, NO3-1. They're both aqueous because they came from something aqueous. Then we have to fill in how many of each. 1 copper, 2 nitrates. Our last thing is our silver solid. We leave solids, liquids, and gases alone, so we don't do anything at all to our silver. Again, I'll put a little 0 here for emphasis. That's talking about the element silver. Now we would go to cancel out our spectator ions, anything that's exactly the same on both sides of the reaction. I see nitrates are the same on both sides, but our coppers and our silvers are not the same. On the left-hand side, we're talking about the element copper, neutral element solid copper. On the right, we're talking about the +2 aqueous dissolved in water kind of copper. Those are not the same thing. For our silver, we are starting with the +1 dissolved in water aqueous ion, and on the right-hand side, we're talking about the neutral element solid silver. So neither one of those can cancel out. When we go to do our net ionic equation then, we would have our 1 copper, that's a solid, and just for emphasis, neutral. We're going to add to that 2 silver ions that are aqueous, arrow, 1 copper +2, aqueous, and 2 silver, elemental silver. So these guys, my element copper on the left and my element copper on the right, or silver on the right, are both neutral. In that net ionic equation, the copper on the left doesn't have a charge, but the copper on the right does, has a charge of +2. So if on the left-hand side it used to be neutral and now it's +2, that means that it lost 2 electrons somehow during the course of the reaction. When atoms lose electrons during the course of a reaction, we call that oxidation. We would say the copper has been oxidized. When we compare the silver on the left with the silver on the right, the silver on the left is +1, and then the silver on the right is neutral. So if it used to be +1 and now is neutral, it must have gained 1 electron. But where did the electron come from? Well, when the copper loses 2 electrons, there are no magic wands in chemistry. You can't just make electrons disappear. They have to go somewhere. So the copper gives away 2 electrons, but to who? The copper gives it to the silver. And so we see that the silver gains 1 electron. Gains 1 electron each. There are 2 silvers. So the first silver ion gains 1 electron and turns into neutral elemental silver. Then the second silver ion gains that other electron that the copper gave up and turns that one into neutral element silver. So we're going to do that gain of 1 electron each. We're going to multiply it by 2. So we'll say 1 electron each. I'll write a gain of 1 electron each. But because there are 2 silvers, we're going to say that there is a gain of 2 electrons in total. Whenever a substance gains electrons during the course of a reaction, we call that reduction. We'd say the silver's reduced. If you're thinking that's a little weird, gaining something is called reduction. It's because the charge is reduced. That's where it gets its name from. It used to be +1, and then the charge is reduced down to neutral. So when you're looking at your electrons lost and gained, your total number of electrons lost and your total number of electrons gained. So this number, total lost and total gained, should always equal one another because those 2 electrons, it's the same 2 electrons. We're not talking about 4 electrons in total. It's 2 electrons in total. They just move from the copper to the silver. So if your total lost and total gained don't equal one another, something in your equation is not right.